You know many things about derivatives, but let's have some exercise where we can practice. Let's study this function. If x is equal to 0, because of this term, the value of the function will be 0. If x is equal to 1, because of this term here, the value of the function will be 0. And if x is between 0 and 1, then both of these terms are positive, so the function will be some positive function. Maybe the function could look like this. Well, actually, if we look at these points here, the graph of the function cannot look exactly like this. Function x maps to x cube, it looks like this, and the function x goes to x squared looks like this. These curves are flat near the origin. The derivative of this function is 0 in the origin. So it must be that our function also has similar kind of features near these points. Well, this function here is almost like x squared, but just this x has been replaced by some other variable. Instead of x, we have there some 1 minus t, or better to say it this way. If t is equal to 1 minus x, then the second term here is t squared. So it seems that the graph of our function must look something like this. Let's now study this graph more. For example, we want to find that where is the maximum of this function. Then we want to know if there are some inflection points. It means some points like maybe here could be one inflection point. If we draw the tangent to that point, then the tangent will be cutting this graph in such a way. Inflection points are such points that the second derivative of the function is 0 there. So let's check for the maximum value and the inflection points, and then draw a better graph of the function. And for the maximum value, of course we have that the derivative of the function in this point here will be equal to 0. So we want to find these places where the first derivative is 0 or the second derivative is 0. Here is our function. We calculate the derivative by the product rule. The derivative of x cubed is 3 times x squared, and we keep the second term here untouched. And then we do the other way around. We take this term here and differentiate that, and the power 2 will drop to the front, and the power will be decreasing by 1. So that's almost correct, but we have this inner function minus x here, and its derivative minus 1 will come here. This differentiation went nicely. Let's gather up some common terms. We have here the term x squared, and it seems that we can take this 1 minus x also as a common term. Let's gather them here. Then in the brackets what we will have this term, and from the second term we'll get minus 2x. And we can a little bit simplify. Now the question is that when is the first derivative 0? Well, if we set the first derivative to be 0, then one of these terms has to be 0. And we get 3 points. We get the point 0, 1, and 0.8. So the derivative will be 0 in the endpoints and in the point x equal to 0.8. Next question. What is the second derivative and when is the second derivative 0? Here's our function and here is the first derivative, what we just calculated. We would need to calculate the second derivative. The first term of the first derivative will give by the product rule these two terms. The second term of the first derivative will be giving by the product rule these two terms. It seems we got two equal terms here. Of course, that is not a coincidence. After simplification, this is what we get. It seems that we can take 2x as a common factor to the front, and we will have something in the brackets here. We can simplify it, and we will get some second degree polynomial. For the second derivative of f to be 0, we would have to have that x is equal to 0, or this term here is 0. In the latter case, we can use the formula for this second degree equation. And slowly we will get this kind of value. Well, we can calculate some approximation by hand. So either x is equal to 0.15 or 0.85. So we can put the values of x here. The first option is that x is equal to 0.15 and the second option is that x is equal to 0.85 approximately. So the maximum point for us is x equal to 0.8 and the two inflection points of this function when x is between 0 and 1 are approximately these points. Let's still calculate the value of f in the maximum point. What is f in 3/5? Well, we will have something to power 3 and something to power 2, and we can calculate what this gives. It gives about 1/30. So here is a nice graph for our function. The function will start from 0 and it will be increasing. Then there's an inflection point. The function will be increasing but slower and slower increasing. Then it will attain its maximum value. Then the function will be decreasing and there's an inflection point. The function will be still decreasing but more slowly and slowly decreasing, and then it will like steadily go to 0 here.